topic of the little talk here is real-time analysis in Carmenta's geospatial technology. So first of all, then, Carmenta's geospatial technology, what's that all about? Well, I like to put it like this. We create technology that help you visualize and analyze geospatial information. That's what we're all about at Carmenta. And when we say geospatial information, we're not only talking about the maps. That's a big part of what we do. The detailed 3D map that Jonas used in his demo was, of course, an important building block in doing this kind of analytics. But it's not only about the background maps, it's also about all the dynamic real-time information that you're feeding into your system, such as your localized vehicles or live data coming in from a radar or from a video feed from a camera onboard a drone, for example. We are very good at bringing this kind of information together and then creating a complete picture that helps out with bringing situational awareness to the users. Not only by actually visualizing the data, but also by performing analysis to help the end users figure out what is actually going on in the map. Looking at our technology, then, a few of the sort of benefits that you get from integrating Carmenta into your system. One thing which is really important for us is that you should be able to directly access your geospatial information directly from the source. We strongly believe that if you have to convert or pre-process your data to get it into your system, then, I mean, it will be much less operationally useful. So we've built in support for reading a large amount of data formats, both traditional GIS formats. Of course, we're really good at connecting to various web services. On the 3D data side, you can throw like 3D tiles or Collada models or OpenFlight models at us, and we'll read and visualize those and use them in our analytics engine without any sort of pre-processing. But it's not only about the data, it's also about all the dynamic data sources. And our SDKs, our software development kits, are designed to make it really easy to bring in dynamic data sources, like, as I said before, like video streams or radar plots or whatever that kind of dynamic information can be, and visualize it together with the background maps. A final important thing for us, I know that there are a lot of GIS people out there, interoperability is really key for us, and it's at the core of how we design our software. We love the OGC, the Open Geospatial Consortium. We're an active member there. We're right now participating in the ongoing OGC meetings that some of you might be familiar with. We're looking at the new OGC APIs that are in the process of being defined. So we love interoperability. We really want our solutions to work well with other software out there. Okay, so that's briefly about the technology. Then going in a bit more into detail on the product side of things. The main product that Carmenta provides is something that's called the Carmenta Engine. And the engine is an SDK. It's a software development kit that allows you to integrate functionality into an application, like was the case with the sighting tool that Jonas showcased. You can use a lot of different programming languages, as you see here, to actually do that integration. So we're trying to stay quite open there. And also on the deployment side of things, you can deploy this on anything from a simple Android device like a cell phone to a high-end workstation. And the functionality is equivalent across the range. So you can do the same sort of analytics that you see in the sighting tool. You can do that on an Android tablet out in the field, for example. But of course, there's not only traditional applications. You can also do web-based mapping. So we have a product called the Carmenta Server, which is an encapsulation of this technology. But instead of providing programming APIs, it provides ways to access the information via web interfaces, standardized interfaces. And you can install this as a traditional server, or you can use it in a Docker container environment. We provide a version called the Carmenta Server Core, which can be deployed in a Docker environment right out of the box. So that's a bit on how you can actually get access to our technology. But yeah, it's getting too much PowerPoint here and a little too little actual demos. So let's jump into the analysis functionality then. First off, what you've seen examples of so far is the component that we call the visibility analysis toolkits. And yeah, let's just jump right into a demo of this functionality. So I'll try to walk you through what kind of functionality we have in our toolbox for looking at intervisibility between objects. So I'm switching over now to an application. It's called Carmenta Explorer. It's a way to preview Carmenta map configurations and play around a bit with them and try them out. So it's what I'm using for demo purposes here. Carmenta Explorer is included in our SDK, in our software development kit. So we have a map here. We're somewhere up in Northern California, Lake Tahoe, for those of you who are familiar with this region. So I've got some different data sources loaded in here. It's a mountainous area, so it's a fun place to be for doing visibility analysis, right? And you can see a bunch of eyes here. If I hover them, they're different observers. So I've got a bunch of observers that I can move around in the map here. So okay, so we have an observer and we want to figure out what that observer can see. So what kind of functionality do we have for that? Well, the traditional way of visualizing intervisibility is to calculate a so-called view shed, which shows you what you can see from a certain vantage point. So as I move this observer around, as I change its altitude, we can dynamically calculate what you can see in the surrounding terrain. And that's all good and well if you want to observe something on the ground. But that's not really the counter UAS use case, right? What's coming at you in that use case is something that's above ground. So intuitively, we can sort of figure out that from this observation position, someone could sneak up at us from behind this hill here, and we wouldn't be able to spot that thing. We can see that there's a maximal range of this observer, right? Because we can sort of see a circular shape here. I could actually just show the outline of that shape here. That's the dome that constitutes the maximal range of the observer. But it's still very hard to figure out what I can actually see behind the hill here. If there was something over there, could I then see him? Well, no, I couldn't. This is actually another type of analysis that's part of our visibility analysis toolkit. The blue dots that you see here are targets. And as I move the targets and observers around, we'll calculate in real time which observers can see which targets. So if I'm up here with my observer, I can actually spot that thing which is behind the hill here. But if I'm a bit lower down, then the visibility is interrupted. And this is, as you can see, all done in real time as the objects are moving around. This target line of sight functionality is really designed to be connected to a live data stream where you have sensor data coming in and you want to figure out the intervisibility really rapidly. It can do hundreds of calculations a second, figuring out point-to-point intervisibility. So that's what we call the target line of sight. But okay, a better way maybe to visualize what you can actually see behind the hill here would be to calculate the actual volume of sight. So that's another feature of our line of sight analysis then, is the ability to generate these volumes. And that's exactly what Jonas showed you in his demo. So the actual coverage of this sensor visualized as volume. And if I go down a bit in this map here, we will see that there is actually an area underneath here where they cannot see, as it's kind of expected since it's behind the hill over there. And just like our other types of line of sight, this is a very rapid calculation. It's recalculated in real time as I'm moving this observer around. Finally, then, what we added relatively recently to the technology is something which we call the airspace coverage analysis. And that is also what is utilized in the sighting tool. So rather than looking at the individual coverage of each observer, you're looking at the combined coverage within an area of interest. So up around this little lake up here, we've defined an area of interest. So this is the area that we want to cover. We've got two different observers here, as you can see. I'm now visualizing the maximal range of those two observers. But of course, based on just this visualization, it's hard to figure out exactly what I'm covering here. Are there areas down by the lake here that I'm not covering? And that's what the airspace coverage calculation can tell us. So based on the observation positions here, we're calculating in real time what you can see from those, in this case, 2 vantage points. And related to that then, as Jonas explained, sometimes it's interesting to know where you have good enough coverage, defined as coverage by a certain number of sensors or coverage by sensors of certain types. And that's also something that can be outputted from this analysis in real time. So just as a very basic example, then here is the dual line of sight. So this is the area where I have coverage with at least 2 of my observers. As I move them around, you'll see this little thing in the middle here, updating. Were I to move the 3rd observer over here, to move it up here, of course, the covered area would increase a lot, since I now have 3 different observers to play with. So that's a bit of examples on how you can work with different kinds of visibility analysis in our toolkit. So just a quick summary of what we saw then. The target line of sight tells you which observers can see which targets. The viewshed analysis tells you which part of the surrounding terrain you can see. The volumetric line of sight focuses on the airspace around you and tells you which part of that airspace you can see. And finally, the airspace coverage focuses on an airspace of interest and a number of different sensors and figures out the coverage within that area. So there's a lot to play with here in our technology when it comes to doing these kind of coverage calculations. But since we're a bit short on time here, I will not elaborate more on that specific feature. I thought I'd show you one more analysis, which can be useful in a use case where you want to deploy your sensors out into the field, and when you have limited time to do so. So that's a separate set of analysis that's included in our toolkit, which we call the terrain routing analysis. And yeah, well, let's just look at a demo of that one as well, right? It's easier to showcase than to do PowerPoint. I'm going to open up another little example here. So as you can see, we're pretty much in the same area, still Lake Tahoe here. But in this case, we have defined a set of waypoints, which we want to access with our vehicle. And the cool thing about this terrain routing analysis then is that it can calculate a route for a off-road vehicle that can also go outside the road network. So it takes the vehicle characteristics into account, and it can figure out how you can traverse from one point in the terrain to another. And of course, to do this kind of analysis, you need a bunch of different data sources, obviously. The satellite imagery is not enough to figure out where you can go, even though you can sort of figure out that, yeah, this looks like a pretty open land. There are no trees here. That should be a good area to traverse, right? No, of course, we need the elevation data. Oops, there's a bit of a hill here. Wonder if our vehicle can traverse that. Of course, that's one part of the vehicle characteristics, then, the maximal slope that it can support, both going horizontally and also the side slope. So, okay, so the elevation data is one important input to this calculation, but we need more, of course. There's a forest here. Probably we don't want to go through that forest with our vehicle, right? So the land use data is another important input. So we're sort of colorizing the map here now to indicate whether it's a forest or open land or swamp and so on. So the elevation data and the land use data, it will give us sort of no-go areas where we know that we will not be able to reach them with our type of vehicle. Let's highlight those in the map. Well, you see the water is off limits. The waterlogged areas, the swamps down here, are also off limits. And then large parts of the terrain are off limits due to the slope. It's simply too much slope. But fortunately, our first waypoint here is placed so that we can actually get out of this slope here. That's an interesting coincidence. Of course, there's something missing. We need the road network as well, because if there's a road, then you'll drive on the road rather than on the field next to it, obviously. So this is the input that's required, and the calculation can then tell us how to go from A to B to C in the terrain. And based on the vehicle characteristics, it'll also tell us approximately how long it'll take to go from A to B to C. So in about 11 minutes, I could actually get up to that position. So it's a pretty cool calculation that helps you out a lot when you have a scenario where you need to go out into the terrain, for example, to deploy a sensor for your counter UAS installation. And as I said, the vehicle characteristics is a big input to this. So you're sort of modeling your vehicle in terms of the different terrains that it can support and the different slopes and so on. So that's a basic just routing calculation that tells you how to go from A to B to C. But the cool thing about this analysis is that it's performant enough that it can analyze how far you can go in any sort of direction. So if we turn off the route, I can turn on something called the accessibility calculation instead. So we're now sort of colorizing the terrain here, right? And the colors indicate minutes from the start point, which is up here. So bright yellow means that I can get to that point in less than 10 minutes. Yellow means 10 to 20 minutes, and so on. And you can see as I move this starting point around here, we're recalculating these so-called isochrones. If you're familiar with GIS analysis, you will know that this is called an isochrone, Latin then for equal time. So it tells you how the areas and the colorizations are based on the same amount of time being required to go to that point. If I start to move the starting point into the city center here, since there's a dense road network, I can get pretty far in those 10 minutes. Whereas if I go up into the terrain here, then I'll get much shorter in that allotted time. So just another example of an analysis that's built into the toolkit. And going back to the first example that we saw here with the visibility analysis, well, of course, you could use this type of calculation also in this scenario. So say that you have your base over here, for example, and then you want to know whether you can get into a certain point into the terrain to deploy your sensor in time to catch any incoming UASs, for example. Then doing this type of analysis and combining it with the visibility analysis can be a real game changer for analyzing the deployability here. So another little example of an analysis that's built into our toolkit. So what you saw in this demo, then, to summarize, you saw the route planning functionality, which essentially tells you what the optimal way to get from A to B is. And you also saw an example of the terrain accessibility. How far can you get in a certain amount of time based on a certain starting point? So yeah, two examples of geospatial analytics, and also both of them are a bit tied to the counter UAS use case. Of course, in our technology, we have a lot of other features which are used by customers in the UAS domain. We have a lot of different customers in this domain. Counter UAS is one very interesting use case for us, but also we're being used a lot in ground control stations for drones, where you have a need to give the situational awareness to the pilot using terrain data, land cover data, and other data sources. So we've done a lot of things in the technology to enable those kinds of systems as well. For example, it's extremely easy to get aeronautical data into your system directly in the distribution format, be it ARINC 424 or AIXM, which is standard formats that are used by organizations such as FAA or Eurocontrol to distribute, for example, restrictive airspace and control zones. You can directly connect to those kind of data sources and visualize them like this, like an aeronautical chart with the different airspaces, with the different routes and so on. And that's sort of all read and visualized on the fly. And of course, it can be used as an input. You could take a control zone from the aeronautical data feed and use that as your analysis area for your airspace coverage analysis, for example. Finally, what's used a lot in the drone context is our ability to georeference video streams in real time and overlay them onto your maps. So let's look at a quick demo of that as well. This is the last demo, I promise. I probably overran my time slot already, but okay, so this is a 2D map showing a video stream overlaid. Let's switch to a 3D presentation of that as well, because that's a bit more interesting, I think. So here you can see a 3D environment using an orthophoto and then some building outlines. And the reason the building outlines are interesting in this demo is that when we're displaying the video feed in a 3D map like this, we're actually projecting it onto your 3D environment, which means that you will be able to analyze very clearly where you have gaps in your coverage of your video feed, for example, due to the placement of the camera and so on. And as you can see here, it's the full HD stream from the drone video here that's been played back onto the background map in real time. So another example of how you can use our toolkit then with UAS data sources. Okay, so that was a quite brief, but I hope interesting introduction to our toolkit and some of the cool features that you can use to do analytics and visualization. So thanks a lot for listening into this little part of the presentation. I hope there are lots of questions that have popped up during my little talk here now, and I'll be happy to answer any questions that you have. Get this.